In my last video, I showed how we can solve differential equations using anti-differentiation. And I talked about a set of solutions, a set of answers. And what I meant by that is the plus c in every single one of these answers is providing us with a whole family of functions, right? Ordinarily, the plus c represents some sort of vertical shift in a function. Y equals some function of x, and then plus a constant is going to be a vertical shift. But we can see that picking different c values here is not going to be a vertical shift because of that constant, because of the coefficient on the linear term. And on that the example we ended with at the last video with the x squared plus y squared equals c. Again, this is something where changing the c value is not going to be a vertical shift. It's going to change our equation some other way. But picking different values of c will give us different particular solutions to the original differential equation. So the general solution will have the c, the constant of integration, in there. And then if we have some sort of initial condition, then we can solve for c. This is not anything new. We've done this a lot with derivatives in the past. So if I tell you that not only our particular solution differentiates to secant squared of x, but also passes through the point pi over 4 comma negative 1, then we know that the x value of pi over 4 gives us a y value of negative 1, which means that I can substitute a y with a negative 1, and I can substitute an x, all the x's, with pi over 4, and the only thing left that we don't know is the c value, the constant, but we can solve for that constant. We know that the tangent of pi over 4 is 1, and if we solve for c, we're going to get negative 2 equals c. So while the general solution is y equals tangent of x plus c, the particular solution that passes through the point pi over 4 minus or comma negative 1 is y equals tangent of x minus 2, because c equals negative 2. And that's an extra step that we're often going to have to do. It'll be a little bit more involved in this next example because we have two different constants to solve for. That means we're going to need two different initial conditions. So when we try that, we're going to see that we're going to have to use this x-y pair to get an equation with c1 and c2, and this second xy pair to get a second equation with c1 and c2. So I'll kind of blast through the algebra here. Y equals 2, x equals 1, 1 squared is 1, 1 cubed is 1, 1 plus 1 is 2, subtract 2 from both sides, we get 0 equals c2 plus c1. That's the equation we get when we substitute 1 and 2 in for x and y. Do the same thing with 3 comma 4. We're going to let y equal c2 plus, this time x is equal to 3, so we have 3 times c1 plus 3 squared plus 3 cubed. 9 plus 27 is 36. Subtract 36 from both sides, we get negative 32 equals c2 plus 3c1. We know that c1 plus c2 is 0. Therefore, we know that negative c1 is equal to c2. This came from here. So because negative c1 is equal to c2, we can replace c2 with a negative c1, just a little bit of substitution there. And we'll get 2c1 is equal to negative 32, or negative 16 is equal to c1, which means that c2 has to equal positive 16. So our particular solution is y equals 16 minus 16x plus x squared plus x cubed. It has a second derivative of 2 plus 6x, and it passes through these 2 points. This would be an easy thing to check in a graphing calculator. Likewise, we can take a look at a solution that not only satisfies this differential equation, but also passes through this point. we will do the same thing, right? We're going to take that x and that y that we're given, and we're going to substitute them into the equation. So the x squared becomes a 4 squared. The y squared becomes a negative 3 squared. Of course, we don't forget that parentheses around the negative 3. And we don't know what c is, but we do know what c is because we know that 16 plus 9 is equal to c, or 25 is equal to c. Therefore, we have x squared plus y squared equals 25 as the particular solution to this differential equation that passes through the point 4, negative 3. I encourage you, if you don't already know what the graph looks like, give this a try, graph this function, and then you should recognize what you get, and imagine what you get with different c values as well. So different initial conditions are going to give you different c values, and you can start imagining what all the different solution curves of this particular differential equation might look like. Definitely worth your time to explore that. We'll do that more in the following section when we look at differential equations graphically. All right, but we're going to move on to a different example now, different differential equation. Dy dx equals x squared divided by y. Okay, we're going to try to find the particular solution that passes through each of these given points, and then use a calculator to graph each particular solution in the same window. So, first step would be to separate the variables. This is going to separate the same way that third example above separates, right? We're going to multiply by y on each side. We're going to multiply by dx on each side. And then we're going to take the antiderivative of both sides. And when we do that, we get 1/2 y squared equals 1/3 x cubed plus c. And we could leave it like that if we felt like it, but I would rather probably get rid of all the fractions if I can, or at least get rid of the 2 over here. I don't really care about this fraction, but just keep the y side as simple as possible. So maybe I'll multiply both sides of this equation by 2. We could multiply both sides by 6 if we really wanted to get rid of all the fractions. Whatever your preference is, really. So, and we end up, in this case, we end up with y squared equals 2/3 x cubed plus c. Now, again, we could take the square root of both sides and get y equals the square root of all that. But then we would lose half of the solution, right? Because we would have only the positive version. And we might want to say, well, we could use a plus or a minus. Then we have 2 different equations, and then that gets a little bit messy. Again, that's an option. I'm going to leave it like this, though. So for each of these initial conditions, I'm going to solve for a new c value. So for the initial condition, -2, 0, we're going to let y equal 0. And we're going to get 2/3 times -2 cubed plus c. So c is going to equal, I guess this is going to be a -16/3 that we're going to add to the other side. So I guess we'll get 16/3 equals c. So our particular solution would be y squared equals 2/3 x cubed plus 16/3. Okay, kind of a strange looking answer, but an answer. We'll do the same thing with this. I'll just kind of blast through these because this is just arithmetic, and at this stage of the game, I think we all know arithmetic. That's exactly the point in time when I start making mistakes, when I say we all know how to do this, and then I make a mistake. But hopefully these are correct. We'll double check them in a calculator momentarily. Let's get some new colors in here for fun. 0, 0, we'll get 2/3 0 cubed. So that means that 0 equals c. So we get y squared equals 2/3 x cubed. And then finally we have 0 equals 2/3 times 1. Oh, I need to change colors. Sorry. Can't do 2 problems in the same color. That would be weird. Yeah, so 2/3 times 1 cubed plus c. This times c is going to be a negative value. Okay, so y squared equals 2/3 x cubed minus 2/3. All right, and I'll pull up some graphs so we can take a look at each one of these solutions. And you'll notice that with, excuse me, with this graph, this collection of graphs, the blue one is this curve right here that goes through the point -2, 0. The green equation is the one that goes through the point -1, 0, and you'll notice that 0, 0 and 1, 0 are also being traveled through by their respective particular solutions. So these are 4 different particular solutions of the differential equation, and you can imagine changing the initial condition to any other initial point, and it doesn't have to be a point on the x-axis, but I picked those just because those are easier to calculate. And one thing to notice with these solution curves is that they don't intersect each other, and we can kind of fill the entire Cartesian plane, the xy plane, with a whole bunch, an infinite number of these solution curves, and none of them are going to overlap. They're all going to be following their own unique path through the Cartesian plane. And that's going to be a nice thing to think about when we get into the graphical approach to these differential equations.